right? So if we consider two sources which are coherent and in phase with each other, then you get an interference pattern like what you see on the screen. So at the point O, because the point O is equidistant from S1 and S2, you will see a maximum forming. They interfere there with a path difference 0, phase difference also 0. Therefore, constructive interference, you'll see a bright spot or a bright band. Yeah, Pradyun, you can. Okay. Now, as you move away from O, alternately, you'll be getting dark and bright bands. That is fine. Now, if you consider any position on the screen, okay, any distance on the screen, let's say this one, fine. From this perpendicular bisector of the sources to that point on the screen, let's say the distance is y, right? And two waves will be arriving at y, one wave from S1 and one wave from S2. Okay, y is a random point on the screen. You can imagine the wave from S1 like this and the wave from S2 like this. They have a certain path difference clearly. Okay, they don't travel equal distances. And how is y related to that path difference? Y is equal to delta x capital D by small d. That's the path difference. Okay. Uh, Understand this carefully. Let's say the wave from S1 travels a distance x1 to reach that point. Okay, we can call the point as P. And the wave from source S2 travels a distance x2 to get there. Fine. S1, S2, the sources are in phase, but because the waves travel different distances, they will arrive there with a phase difference. And we already know the relation between path difference and phase difference. Delta x divided by delta phi, okay, path difference divided by phase difference is wavelength divided by 2 pi. So the phase difference with which they arrive there will be 2 pi delta x divided by lambda. Okay. Now we have a relation between y coordinate and the path difference with which the waves arrive there. Using this, you can derive a relation between y coordinate and the phase difference with which the waves arrive there. How is that useful to us? If you know with what phase difference the waves interfere at a particular point, then you can tell what is the effective amplitude at that point, what is the effective intensity or brightness that you see at that point, and such things. Okay. Basically, this is a pattern of varying brightness. Last class we had seen a picture of the YDSC pattern also. I'll show it to you once again. Yeah. So you get a pattern like this of varying intensity, bright band, and gradually the brightness decreases to 0. Dark band, again gradually it increases, again gradually. But this happens, you get completely dark bands if the sources S1 and S2 are of the same brightness, same intensity. Okay. So if you know with what particular phase difference the waves arrive at a point on the screen, you can comment on the intensity at that point. I mean, in cases where the sources are of the same intensity, you will also be able to find out the intensity at that point in cases where the sources are of different intensities. Okay. So those detailed calculations are what we are going to discuss today. Fine. So we have a relation between y and delta x. Using that, we'll form a relation between y and phase difference. So y is equal to, in place of delta x, you can write delta phi lambda by 2 pi. Okay, that is in place of delta x, and capital D by small d. This is the relation between the distance on the screen from the central maximum, or from the perpendicular bisector, I should say, and the phase difference with which the waves arrive there. Fine. Let's consider this situation. First, suppose the source S1 has intensity I, and the source S2 has intensity 4i, means the sources are not of equal brightness. Now, how we create such sources and all we'll discuss. Okay, but let us do all the calculations first. The proper experimental setup we'll discuss at the end. So S1's intensity is I and S2's intensity is 4i. Okay. Consider the central maximum. Rishi, can you tell me with what phase difference they interfere at central maximum? Central maximum is the point O. With what phase difference do they interfere at the point O? Since O is on the perpendicular bisector of S1 and S2, the distances traveled by the waves to get there will be same. So path difference is 0, automatically phase difference becomes 0. So at the central maximum, the phase difference between the interfering waves is 0. Okay. Now, if two waves, fine, if two waves having amplitudes A1 and A2 undergo interference with the phase difference delta phi, then the effective amplitude, okay, after they interfere, the effective amplitude is calculated as root A1 square plus A2 square plus 2 A1 A2 cos that phase difference delta phi. And if the waves have intensities I1, I2, then if they interfere with a phase difference delta phi, the effective intensity is calculated as I1 plus I2 plus 2 root I1 I2 cos delta phi. In the intensity formula, cos delta phi is outside the square root. We had discussed this at the beginning of this chapter itself, basic wave properties. So using this formula, you can tell what is the effective intensity that you can expect at any point on the screen if you know the phase difference with which the waves arrive at that point on the screen. Okay. Now at the central maximum, the phase difference delta phi is 0. Therefore, effective intensity at central maximum will be I1 plus I2 plus 2 root I1 I2 cos 0. Cos 0 is 1, so need not mention that. And we are considering the sources have intensities I and 4i. So I1 is I2 is 4i. Just substitute there. I plus 4i plus 2 root I1 I2 is I into 4i. I into 4i is 4i square. Under root 4i square is 2i. 2 into 2i is another 4i. So effectively the intensity you get becomes 9i. Okay. Individual sources had intensities I and 4i, but if they undergo constructive interference at a particular point on the screen, you will see an intensity of 9i. Okay. What does this mean? Like experimentally or practically, if you talk, suppose we cover one of the sources. Let's say only S1 is present, S2 is not present. S1's intensity, we took it as I. Then it will create this a uniform intensity on the screen. Okay. You will see the same intensity I everywhere on the screen if only S1 is sending waves. Next, S2's intensity is 4i. Suppose you switch off the source S1 and allow only S2 to produce light. The light that falls on the screen from S2 will create a uniform intensity of 4i, uniform brightness of 4i on the screen. So if only S1 source is switched on, you'll see intensity I on the screen. If only source S2 is switched on, you'll see intensity 4i on the screen. But if both are switched on at points where constructive interference happens, okay, we derived at central maximum where phase difference is 0. But even if phase difference is 2 pi, 4 pi, 6 pi, any even multiple of pi, you will get this same intensity of 9i. So at points where constructive interference happens, means at points of maxima, okay, the red dots that I have marked on the screen, at those points, the intensity will be 9I. Okay, that is what this shows. Next, at any minima or at any minimum, minimum means what? The point, a point on the screen where the waves undergo destructive interference. For minimum, the phase difference should either be pi or 3 pi or 5 pi and so on. Basically odd multiples of pi. So at any point of minimum or position of minimum, the effective intensity becomes, see, I1 is I, first source intensity is I, second source intensity is 4I, I2, plus 2 root I1, I2 cos phase difference. Phase difference is an odd multiple of, okay, in intensity formula, the root does not extend to the cos. Phase difference. Phase difference is an odd multiple of pi. Okay. Now, odd multiple of pi, whether it is cos pi or 3 pi or 5 pi, becomes minus 1. Cos of an odd multiple of pi is minus 1. Now see what happens to the intensity. You get I plus 4I plus root of I into 4I is 2I. 2 into 2I is 4I with a minus sign. So minus 4I. Therefore, at minimum, the intensity you see is I. You won't see a perfectly dark spot at the minima. You will see minimum intensity there, that is I. So what effectively happens is, in the pattern, the bright spots will have intensities of 9I, and the dark spot, I should not call it dark because some intensity will still be seen. At bright spots, the intensity will be 9I at maxima. At minima, you will still see some intensity and it's only I. That is what the calculation shows. Fine. So if the sources are not of equal intensity, they won't cancel out perfectly on the screen. Or not just on the screen, they can't cancel out perfectly anywhere. Rishi, is this clear?
Yes, sir.
Okay. Try this question now. Suppose the first source, okay, have you noted this formula for intensity, effective intensity?
Yes, sir. I've noted it.
Okay. Suppose the source S1 has an intensity, okay, let's say the sources have equal intensities, S1 and S2. Have intensity or they are of intensity I each. Okay. Then first, how much is the maximum intensity that you can see anywhere on the screen? Next, how much is the minimum intensity that you can see anywhere on the screen? Rishi, tell me, what kind of interference gives you maximum intensity? Constructive interference or destructive interference? Or is it something else?
Constructive.
Constructive interference, correct. And for constructive interference, how much or what should be the phase difference with which they interfere?
0, sir.
0 is one possibility, 0 or 2 pi, 4 pi, and so on, even multiples of pi. And when can you expect minimum intensity on the screen?
During destructive
Destructive
interference.
interference, and for that, the phase difference should be pi, 3 pi,
Uh,
5 pi, odd multiples of pi. Okay. So you use the formula for effective intensity and tell me what are the maximum and minimum intensities in this case. Okay. Let's solve. What is the formula for effective intensity?
I1 plus I2 plus root of I1 2 root I1 I2
2 root I1, I2
cause
phase difference with which the waves interfere. Okay. And this is valid only for two waves. Fine. One wave of intensity I1, another wave of intensity I2 interfering. Fine. You just have to substitute the given intensities. How much are I1 and I2?
I, sir.
I. So you get I plus 2 root I into I. Root of I square is I itself, cos whatever is the phase difference. Okay. So effectively, I mean, in this situation, because the intensities, individual intensities are I and I, you have to do this calculation 2I plus 2I cos delta phi. Okay. Now the first part, intensity at maximum. You know what is the phase difference for maxima? So you get 2I plus 2I cos any even multiple of pi you can take, and cos of any even multiple of pi is 1. Then the answer should be 4I. How did you get 5I?
Sir, I got I added some I randomly. I got
Okay, fine, fine. Next, intensity at the minima. Wait. Rishi, are you able to see the screen in? Okay, wait. I don't
yes,
think
sir.
this will. Fine, let it be. Huh. So next is intensity at minima. So 2I plus 2I at minima. The phase difference is pi or any even any odd multiple of pi. Cos of any odd multiple of pi will be -1. Then how much is the effective intensity at minima?
Ti
2I plus 2I into -1.
minus 4I.
It becomes 2I minus 2I. Like the -1 is only to the second 2I, no? So effective intensity becomes 0. Clear?
Yes.
Huh. So that is what you see in the simplest case of YDSC. If you take sources of equal intensities, let's say I and I, then at the maxima, you see a brightness of 4I. Okay, this is also interesting. If only the source S1 is switched on, you will see intensity I everywhere on the screen. And if only S2 is switched on, you'll again see intensity I everywhere on the screen. But if both sources are switched on, you will see bright spots of intensity 4I and dark spots of 0 intensity between them. Okay, that is what we call as the interference pattern. So if source intensities are equal, then maximum intensity will be 4I, minimum intensity will be 0. Clear?
Yes, sir.
At points of minima, they cancel out perfectly. You will see a perfect dark spot. Okay. Now at maxima we found out intensity is 4I. At minimum we found out intensity is 0. Now between a maximum and the next minimum, the intensity decreases gradually. From 4I it goes down to 0. Okay. So actually, if you plot a graph of how the intensity varies with distance, it will look like this. High intensity, 0 intensity. Again, high intensity, low intensity or 0 intensity, high intensity, 0 intensity, and so on. On the upper side also, you get a variation. This is how intensity varies. Fine. And in YDSC pattern, remember, all the maxima have the same intensity. Fine. Whether it's the central maximum or the first maximum on either side of the central one, second maximum on either side of the central one, all maxima have the same intensity. And all minima also will have the same intensity. In this case, because we took sources to be of equal intensities, that minimum intensity turns out to be 0. Is this point clear? Okay. Now we know that the y coordinate for the first maximum, okay, on either side of the central maximum is lambda capital D by small d. So central maximum, if you take the distance as 0, then at a distance lambda capital D by small d from it, you'll see the first uh, secondary maximum forming. First secondary maximum. Now in between central maximum and the first maximum, there will be a minimum also. That occurs at lambda d by 2d. That's fine. Now let's take a random y coordinate, say lambda capital D by 4 small d. This does not correspond to a maximum. This does not correspond to a minimum also. I have given you some random y coordinate. Okay, so some random distance on the screen. At this distance on the screen, I want you to find out how much is the intensity that you can expect. How much is the effective intensity that you can expect. And for that, I'll have to give you uh, source intensities. Let's say S1 and S2 have equal intensities of I each. So how much is the effective intensity at this much distance on the screen? Try. Fine. What do you need to know to find out effective intensity? What-
The
hmm,
delta of the phase difference and the intensities of both of them,
Right.
and then
You need individual intensity. That's all. You need individual intensities and the phase difference with which they interfere. Delta phi. Okay. Don't say delta of the phase difference. It's delta of the phase or simply phase difference. Okay. Individual intensities are given to you in this question. Source intensities are I each. All you need to find out is the phase difference with which they interfere at this point. Okay. You are given a particular y coordinate. And this is the standard YDAC setup. So sources are in phase. Perpendicular bisector is the central maximum. Now at this y coordinate, you have to find out how much is the phase difference with which they interfere. Okay. Can you recollect and tell how y can be related to delta phi? What is the relation between y coordinate and the phase difference? Otherwise, tell me this at least. What is the relation between y coordinate and the path difference delta x? Okay. See, you need to like derive this once and you have to memorize also. Y is equal to delta x capital D by small d. This is the relation between y coordinate and the path difference with which they interfere, okay, at that point in the standard YDAC setup. And we know the relation between delta x and delta phi. Delta x by delta phi, path difference divided by phase difference, is lambda divided by 2 pi. When path difference is of one wavelength, one pulse, the phase difference will be 2 pi, one cycle. Okay. So you can write delta x is equal to delta phi by 2 pi multiplied with lambda. That's what we had discussed earlier also today. Yeah. Okay. It becomes delta x into 2 pi divided by lambda. Sorry. Yeah. Uh, yeah, that is for delta phi. This is for delta x. Nothing wrong in this. So you use this relation between delta x and delta phi to convert from one to the other whenever necessary. Now you are given a particular y coordinate, lambda capital D by 4 times small d, and you are asked what is the effective intensity. So you have to relate y coordinate to the phase difference delta phi. Now delta x can be written as delta phi into lambda divided by 2 pi. We are going to substitute that here. That's all. That will give you the relation between y coordinate and the phase difference. So you get y is equal to, in place of delta x, delta phi divided by 2 pi into lambda. That is delta x. And you are still left with capital D by small d. This is how you relate y coordinate to the phase difference. Is this clear?
Yes, sir.
Okay. Now the y coordinate that you are given is lambda capital D divided by 4 small d. That's all. Now cancel whatever you can on both sides. Lambda capital D cancel, small d cancels. That's all. You get the phase difference now. Tell me, how much is the phase difference? Send 2 pi to the other side. It becomes 2 pi by 4. That is pi by 2. That's the phase difference with which the waves interfere at this particular y coordinate. Okay. And if you know the phase difference, you can tell what is the effective intensity now. Therefore, the effective intensity becomes, individual intensities are I and I each. So I1 plus I2 plus 2 root I1 I2. I1 I2 becomes I square cos phase difference with which they interfere. That is pi by 2. And cos pi by 2 is 0. So this whole term, this last term becomes 0. The effective intensity is 2i. Is it clear?
Yes, sir.
Okay. So basically what we found out, or what we derived just now, is if sources are of equal intensities, you know that at central maximum, or whenever they undergo constructive interference, the intensity you get is 4i. Maximum intensity is 4i. Minimum intensity is 0. Okay. Now, the distance from the central maximum to the first point where you get maximum intensity, this is lambda capital D by small d, the fringe width. The distance from central maximum to the first point where you get minimum intensity is lambda capital D by 2d, half of the fringe width. Okay. The distance given to you in this problem was lambda d by 4d, which is this half distance. Okay. There the intensity is neither maximum nor minimum. It is some value in between, and we find that it is 2i. Okay. Maximum intensity 4i, minimum 0. At this particular distance, it is 2i. So did you understand how to find out intensity, effective intensity at any given distance on the screen? You'll be given distance as the y coordinate. Okay. Then you have to relate the y coordinate to the phase difference using this formula. And based on distance, if you get the phase difference, then you can tell the effective intensity. That's the idea. Okay. Next. Rishi, tell me, what is the formula for fringe width in YDSC? What's the distance
The
between?
sine theta is equal to delta x by d.
Sine theta is equal to delta x by d does not have fringe width in it at all. Small d is the distance between the sources of light. Okay, point sources. Delta x is the path difference. Okay, with which they arrive at a particular point on the screen, and theta is the angular position of that point. Sine theta is delta x by d. The equation is valid, but that does not give you fringe width. Okay, let me discuss fringe width now. Just a moment. Suppose these are the sources. S1 and S2. And at a certain distance from the sources, let's say you have placed the screen. The diagram is not to scale. Okay. the first thing you do is, like, to get the proper interference pattern, the first thing you do is draw the perpendicular bisector between the two sources. And wherever that perpendicular bisector meets the screen, you call that point as O. Now, if the sources are in phase with each other, which is what we are considering, okay, standard YDSC situation is that only S1, S2 are in phase. In fact, their intensities are also considered to be equal. Okay, unless otherwise specified, you'll assume their intensities are equal. In that case, you can see that the distance from S1 to O, okay, let's name the sources as S1 and S2. The distance from S1 to O will be equal to the distance from S2 to O. So they don't have any difference in distance. So the path difference is 0. Automatically, the phase difference with which they arrive there will be 0. Therefore, that becomes a point of maximum intensity. And the angular position of this point O is 0 degrees. What do we mean by that? If you connect the midpoint of the sources to this point O, that line makes 0 degrees with the perpendicular bisector. Obviously, it is the perpendicular bisector itself. Okay. So at O, you will get maximum intensity, a bright spot. Fine. Keep moving away from O. The intensity decreases. I am drawing an enlarged view of the pattern. We have assumed sources to be of equal intensity. Therefore, at minimum, the intensity goes down to 0. Where they undergo destructive interference, the intensity goes down to 0. You will see a perfectly dark spot on the screen. Okay. When does that happen? That happens when the waves interfere with a path difference of half wavelength. That will give rise to a phase difference of pi, odd multiple of pi destructive interference. Okay. And that is what you call as a minimum. And keep going away, you'll again get increasing intensity. You'll again get another maximum, maybe okay, somewhere here. And so on. Okay, that is what we had drawn earlier also. Earlier, the maxima and minima were drawn very close. So you could see many maxima and minima. Here I'm showing you only one or two. Okay. So this is another position of maximum. You get another very bright spot here on the screen. And the same thing you will see on the lower side of O also, not just on the upper side. Theta, okay, like you said, sine theta is equal to delta x divided by d. Theta is the angular position of any point on the screen. For example, if you take the first minimum, that first dark spot that you see, the wave arriving at S1 travels a particular distance to get there. The wave arriving at from S2, okay, arriving there from S2 travels some other distance to get there. So they travel different distances. The extra distance traveled by one of the waves is what you call the path difference delta x. And theta is the angular position of that point on the screen. Theta is this angle. Okay, for the central maximum, theta is 0 itself. For other points on the screen, theta will be non-zero. So this angle theta depends on this path difference, obviously. Okay, as you go away from the central maximum, theta increases, delta x also increases. And this is how they are related. Okay, now what is fringe width? Now, if you draw the pattern on the lower side also, at the same distance from O on the lower side, you will see one perfectly dark spot here. Because we are assuming sources to be of equal intensity, they'll interfere destructively and create a perfectly dark spot. So as you move from O to that perfectly dark spot, you see the brightness. Okay. Or okay, let me draw it in reverse itself. As you move from O to that point, you see the brightness falling like this, decreasing like this. And at that point, it becomes 0. Fine. So actually on the screen, it looks somewhat like this, I should say. The brightness increases. And again, the brightness gradually decreases to 0. You see a band like that on the screen. That is what I had shown in the uh, last lecture, that pattern. Did you understand?
Yes, sir.
The variation of intensity? Yeah. This entire band is what you call as a fringe. Fine. And you will see many bands like that. I can extend the screen on the lower side. And here we have, I mean, there's a dark spot forming. Again, at some distance, there'll be a bright spot, and keep going away. At some distance, you'll again get a perfectly dark spot, minimum. Okay. So in between these two dark spots also, the intensity of light gradually increases, becomes maximum. Again, it gradually decreases and becomes minimum. Okay. This is another fringe. And so on. You will see many bands like this, which have maximum intensity at their midpoint, and at the edges, there will be minimum intensity. Each band is called as a fringe. And the width of each band is what you call as fringe width. Now, O is the central maximum. Okay. Let's call this point as A and the point on the lower side as A dash. O to A. See, for A, the path difference is lambda by 2. If path difference is lambda by 2, then y coordinate, we have a relation between y coordinate and path difference, becomes lambda capital D by 2 small d. That's the distance to the first minimum from the central maximum. We had derived this in the last class. We wrote the position of nth minimum also. Okay, go through that once. So this height, I'll remove these unnecessary lines. Just a moment. Yeah. This height or the distance from O to A is that y coordinate lambda capital D by 2 small d. You will see the same distance from O to A dash on the lower side. This is also lambda capital D by 2 small d. Then the total distance from A to A dash, how much does it become? On the upper side, it is lambda d by 2d. Lower side also lambda d by 2d. Then what is the total distance?
2 lambda d by 2.
2 2 will get cancelled. The total distance effectively becomes lambda d by small d. And isn't that the width of the fringe?
Yes, sir.
Yes. Okay. The next fringe also will have the same width. Lambda capital D by small d and so on. This is what we mean by fringe width, the width of each band that you see on the screen. And in YDSC, standard YDSC setup with a flat screen, you will have, uh, you will see all fringes having the same width. Okay. And I told you there's an assumption also. How are you deriving this fringe width? Based on this formula for y coordinate, or based on this relation between y coordinate and path difference. This relation between y coordinate and path difference is valid only if the distance from sources to the screen, capital D, is much greater than distance between the sources, small d. Okay. So if you place the screen significantly far away from the sources, then you will see fringes having equal width. That's the idea. Clear? Okay. So fringe width is given by lambda capital D by 2D. Now, what are the factors on which fringe width depends? Obviously, the wavelength of light used, capital D, the distance between sources and the screen, and then small d, the distance between the sources itself. Okay. Small d is in the denominator. So if sources are brought closer, fringe width will increase. Okay, the bands will become wider. So directly based on the formula, you can tell how The distance between sources or distance between sources and screen or the wavelength will affect the fringe width. Try this question now. I want you to recollect the positions of each maximum, where the first maximum will form, where the second maximum will form. Recollect that once. Okay. And answer this question. The third maximum, or okay, put it this way. If sources of wavelength lambda 1 are used, okay, suppose both sources emit light of wavelength lambda 1, the third maximum is seen at, let's say, some distance y naught on the screen. Where is this distance measured from? From the central maximum O. So at that distance y naught, you are seeing the third maximum. Okay. Now, if the sources emit light of wavelength lambda 2, the second maximum is seen at the same point y naught, at the same distance y naught, where we used to get the third maximum earlier. So if you change the wavelength, no, where you get the first maximum, second maximum, that will change. Fine. So when sources of wavelength lambda 1 are used, we used to get third maximum at one position on the screen. But when sources wavelength is changed to lambda 2, we are getting the second maximum there. Based on this information, calculate the ratio lambda 1 to lambda 2. Okay. Try. Right. When both the sources emit light of wavelength lambda 1, you get the third maximum at y naught. Can you tell me the formula, general formula for nth maximum in YDSC?
Sir, uh, theta nth minimum is 2 n minus 1
Wait, wait,
lambda by 2.
wait. First, theta is the angular position, not the linear position. This question is talking about linear distance y. Okay. I showed you in this diagram, no? Understand this carefully. Let's spend some time with this, not an issue. Or, okay, yeah. You take any point on the screen. For example, you take this first maximum, the red dot that you see at the top. Let's call it as B. O is the central maximum. For central maximum, the number given is 0. It's like the 0th maximum. B is called the first maximum. Fine. And you will have one first maximum on that side of O, and you will have one first maximum on this side of O also. You'll have a point B here, B dash. Okay, there also you can see there's a bright spot. I have shown varying intensity, so that spot is not seen separately, but that is also a maximum. This is also called the first maximum. Let me erase all this. B dash is also the first maximum, and that is on the lower side. Okay, so you'll have a first maximum on that side of O. You'll have a first maximum on this side of O also. Okay, let me erase all these extras also. Fine. At O, they interfere with a path difference 0. That means phase difference is also 0. Obviously, phase difference 0, constructive interference, it's a maximum. At B and B dash, okay, first maximum on that side and first maximum on this side of O, the path difference with which they interfere will be one wavelength. Path difference is one wavelength, means phase difference will be one cycle, that is 2 pi. That also gives rise to constructive interference. That is why you get a maximum there. For B dash also, the path difference will be one wavelength and the phase difference will be 2 pi. Rishi, is this clear?
Yes, sir.
Okay. Now we know y is delta x capital D by small d. For point B, the path difference delta x is lambda. If you substitute lambda in place of delta x, you get y coordinate as lambda capital D by small d. Means the point B is at a distance of lambda capital D by small d from the central maximum. And what is B? First maximum. So the distance, the y coordinate of the first maximum is lambda capital D by small d. You will get the same distance for the first maximum on the lower side also. Is this clear? First
Yes, sir.
maximum forms at lambda capital D by small d. Second maximum will form at the same distance lambda capital D by small d from the first maximum. Okay, you'll get another band there, bright spot there. So this is lambda capital D by small d to the first maximum, and from there onwards to the second maximum, it is another lambda capital D by small d. So what's the distance all the way to the second maximum directly? How much will that be? O to first maximum is lambda d by d. First maximum to second maximum is another lambda d by d. Then what's the distance all the way from O to second maximum? You just have to add the distances. It will be 2 lambda capital D by small d. Okay. Or you could have found it out this way also. For the first maximum, the path difference is one wavelength. For the second maximum, the path difference will be two wavelengths. In that case, the y coordinate becomes 2 lambda capital D by small d. That's the y coordinate of the second maximum. And so on. Third maximum will be 3 lambda capital D by small d. You will get that pattern. So nth maximum will be n lambda capital D by small d. Just a moment. Okay. So you are told that when the wavelength is lambda 1, third maximum is seen at y naught. So you can say that, or we can conclude that y naught is equal to third maximum. So 3 lambda 1 capital D by small d. Is this step clear?
Yes, sir.
Hmm. And then if the sources emit light of wavelength lambda 2, at the same point on the screen, you get the second maximum. So at this same y coordinate, you find the second maximum when the wavelength is lambda 2. That's all. Therefore, lambda 1 by lambda 2 becomes 2 by 3. Is this clear? Fine. You
Yes,
have,
sir. I got that only.
yeah. Let's also discuss the positions of minima and solve one problem based on that. Okay. Uh, Between O and B, there is this point A at which the waves interfere with path difference lambda by 2, phase difference pi. Phase difference pi, destructive interference, you will get a minimum there. Now, if path difference is lambda by 2, it's already marked on the screen. The distance from O to A dash is lambda d by 2d. The distance from O to A on the upper side will also be lambda d by 2d itself. What is this distance? This is the distance to the first minimum. You can derive it using this y-coordinate formula also. For the first minimum, path difference is lambda by 2. You substitute delta x as lambda by 2, you get the distance as lambda d by 2d for the first minimum. Is this clear?
Yes, sir.
Okay. Next minimum. See, first minimum path difference is lambda by 2. First maximum path difference is lambda. After that, you will again get a minimum. There, the path difference will be 3 lambda by 2. Okay. So this is like 0.5 lambda, 1 lambda. Next minimum will be 1.5 lambda. 1.5 is nothing but 3 by 2. So if you substitute path difference 3 lambda by 2, the y coordinate you get will be 3 lambda capital D by 2d. That is the position of the second minimum. Clear? So y coordinate of first minimum is 1 lambda capital D by 2 small d. Y coordinate of second minimum is 3 lambda capital D by 2 small d. Then the third minimum will be 5 lambda capital D by 2 small d. And so on. And here also you can see a sequence. They are all basically odd multiples of lambda d by 2d. So if you generalize this sequence, it becomes 2n minus 1 lambda capital D by 2d. You substitute n as 1. 2 into 1, 1 minus 1. Sorry, 2 into 1 is 2 minus 1 is 1. You get 1 lambda d by 2d. You substitute n as 2. If you want the second minimum, you substitute n as 2. When you substitute n as 2, 2 into 2 is 4, 4 minus 1 is 3 lambda d by 2d, second minimum. Third minimum. You can tell the position of any minimum. Clear?
Yes, sir.
Ah. So this is basically the y coordinate of the nth minimum. So after class, just think of how these formulas were derived. The general y coordinate for nth maximum and the general y coordinate for nth minimum, because questions based on this are very common. Okay. So when wavelength is changed completely for the sources, we know what happens. Okay. Now suppose each source, okay, emits two wavelengths. Fine. Two wavelengths means lights of two different colors. Let's assume the colors are red and uh, green. So situation will be like this. You can consider two sources. Let's say the first source of light is here and the next source of light is here. They are emitting lights of two wavelengths, red and green. And let's say they do that with equal intensity. Fine. And assume there's a screen somewhere here. What will happen? Rishi, what do you expect to see on the screen now?
Two different points
Two different
uh,
points. Huh.
of light, like one from one of the source and the other from the other source.
Mm, see, not one from one source and other from other source. Light from both sources will be reaching every point of the screen. Now, suppose both sources emitted wavelength corresponding to red, only red. Then you would have seen a pattern on the screen. Okay. And a pattern of red dots like this would have been observed on the screen. Let me copy this. Just a moment. You would have seen a pattern like this. Actually, not dots, bands. Fine. Just for our convenience, we are considering them as dots. Is this clear? You would have seen a pattern of red bands. Had only the red, had both the sources been emitting red colored light. Okay. Now, the distance between the sources is fixed, and the distance from sources to screen is fixed. So you'll get this pattern. And what is the distance to the first maximum? Lambda capital D by small d. So wavelength corresponding to red multiplied with capital D by small d. That is where you get the first maximum. And then second maximum at twice this distance, third maximum at thrice the distance, and so on. Okay. If both sources had only emitted wavelength corresponding to green, then what you will see is a pattern of green bands. Rishi, yes or no?
Yes, sir.
Okay. And will the pattern of red bands be identical to the pattern of green bands, or will there be any difference? Will they be identical, or will there be a difference? Will there be a difference?
So there will be a difference.
In terms of what? Or
Intensity.
mm, see, intensity you cannot comment. Like intensity that you see depends on intensity of the sources. Okay, so there may be a difference in terms of intensity. Okay, but mm, in terms of distance between the bands, or in terms of fringe width, or in terms of positions of maximum, will there be any difference? Where the bright bands or the bright spots form, do you think it will be the same for red colored light and green colored light, or will it be different? It will be different, because see, where you get the first maximum depends on the wavelength of light that you are using, no? Yes or no?
Yes, sir.
Huh. So if you change the wavelength, then the positions of maxima will change. Central maximum O will remain there itself, but other maxima, their positions will change. And how will they change? They're proportional to the wavelength. The distance is proportional to wavelength. Now, in the visible electromagnetic spectrum, wavelength corresponding to red color is approximately 700 nanometers. And wavelength corresponding to green, VIBG, green is exactly in between. So between 400 and 700, it is approximately 550 nanometers. So Compared to red, green's wavelength is less. If green's wavelength is less, the distance to the first maximum will be less. So if the red colored light forms a pattern like this, let me just stretch this pattern a little bit. So when both sources are red, assume you see a pattern like this. Then if both sources are green, you see a pattern like this. Okay, I'll draw them side by side. They actually form on the same screen. You see a pattern like this. Okay, the green bands will have what do I say? Shorter width, because fringe width in YDSC is lambda capital D by small d. If wavelength decreases, the fringe width decreases. The bands will become narrow. Is it clear? So suppose the intensity of red color varies like this. Okay, on the screen. So red colored light will be seen on the screen, and along with that you will see green colored light as well. So you will see a combination of red and green. The green light, its intensity will vary like this. So what you see on the screen will be a superposition of these two patterns. Okay, a combination of these two patterns is what you will see. Is this clear? Okay. Now the central maximum will be common to both patterns, because for central maximum the path difference is 0. So whether the sources both emit red or both emit green or both emit any common color, the central maximum will form where it forms. The first maximum for red, okay, will be at lambda red capital D by small d. The first maximum of green will be at lambda green capital D by small d, and definitely they won't coincide because lambda of red is not same as lambda of green. See, I took random wavelengths here. I mean, not random wavelengths. Wavelengths 700, 550 are correct only. Pattern, I drew randomly. It was a freehand pattern that I had drawn. But you can see the first maximum are not coinciding. Rishi, you visually observe the pattern and tell me, is any maximum of red, is any other maximum of red coinciding with any other maximum of green?
No, sir.
It is.
No, the central maximum.
Central is there. Other than central.
The first and last one.
What do you mean first and last one?
Uh,
Number them. Which number of which maximum of red is coinciding with number of which maximum of green?
Sir, third maximum.
Third maximum of red or green?
Red with fourth maximum of green.
What's the number given to the central maximum? Central maximum, the number given is 0. Okay. Then the first red dot you see away from the central one is called the first maximum of red. Then this is the second maximum of red. Okay. Now tell properly which maximum of red is coinciding with which maximum of green.
The second of red and third of green.
Ha. Okay. So second maximum of red appears to coincide with third maximum of green. So questions based on this are also quite common. Okay, they'll give you two different wavelengths. In fact, one of the questions we solved is like this only, but I didn't say both sources emit two wavelengths. Like, where is this? This question. If both sources emitted lambda 1, I said third maximum forms at a particular position. And if both sources emitted lambda 2, I said second maximum is seen at that position itself. So what we have drawn here actually, this pattern corresponds to that problem. You take lambda 1 as green wavelength, green color's wavelength, and lambda 2 as red color's wavelength. Fine. Third maximum of green is forming at the same distance as second maximum of red. Okay, it's a coincidence that this diagram corresponds to that problem, so I'm able to explain better. This is what is happening there. When both sources emitted lambda of green, you would have seen one pattern. Third maximum would have formed at some distance. That distance is called in that problem as y naught. Replace both sources with red colored sources. Second maximum forms at that distance. Now, if both sources emit both colors, both maxima will form at that distance. Okay, so simple idea, if both sources emit multiple colors, you will see a superposition, okay, of multiple patterns on the screen. That's all. Red pattern, green pattern will form together. Is this clear?
Yes, sir.
Okay. And it's also possible that the sources emit white light. Rishi, what is white light?
Normal light.
In terms of wavelength, is there any particular wavelength for white light? Like red wavelength is 700, green wavelength is 550, violet is 400. Is there any wavelength for white light?
Sir, between 400 and 700.
No. It is a combination of all the wavelengths from 400 to 700. White is not a single color. White is a combination of all colors. Okay. So if the sources are emitting white light, it means there are infinite different wavelengths that they are emitting. Now, for each wavelength that they emit, you will get one pattern on the screen. If they emit infinite different wavelengths, you will get infinite different patterns on the screen which are superposed, means which are placed one on top of another or which occur simultaneously. Is this clear?
Yes, sir.
Ha. Now, understand this carefully. When red and green were used, okay, you can see the pattern on the screen. When sources emitted red and green simultaneously, you got a combination of two patterns. And in that combination, there were some positions where the maxima of both patterns coincided. Yes or no?
Yes, sir.
There were some positions where their maxima coincided. Okay. Now, along with red and green, suppose some other color like blue is emitted. Red, green plus blue. Blue color will have another pattern. Blue color's wavelength is even smaller. So blue will have an even shorter wavelength even smaller bands will form. So for blue, we can indicate the pattern like this maybe. Just a moment. Yeah, and blue's wavelength is smaller, so the bands have to be closer. Just a second. Like this. Let's put that pattern also here. Are you able to understand what happens if multiple wavelengths are emitted by the sources? Yes or no?
Sir, can you repeat it?
No, I'm just asking, are you able to understand what happens when multiple wavelengths are emitted by the sources?
Yes, sir. Yes.
Huh. Now see, when red and green were emitted, there were some positions where red-green coincided. Now if red, green and blue are emitted, there will still be some positions where all three coincide. It may not happen uh, over, sorry, it may not happen over here or over here, but you can see at the central maximum, definitely all three maxima are overlapping. Yes or no?
Yes, sir.
Okay. You keep going away from the central maximum. Somewhere on the screen, you will again see all three of them overlapping. Red, the maximum of red, the maximum of green, and the maximum of blue occurring at the same position. That will happen. Definitely at some distance it will happen. So there also all three are coinciding, all three maxima are coinciding. Is this clear?
Yes, sir.
Okay. Now add a fourth wavelength, a fifth wavelength. Add all 7 colors of the visible spectrum. Actually, visible spectrum has infinite colors, but we say there are 7 colors, VIB, GY, OR. Add all colors. What you see is white. Okay. So if the sources emit white light, basically they are emitting, you can assume them to be emitting 7 different wavelengths. Actually, it is infinite different wavelengths, but you can take it as a combination of 7 also. If you add those 7, you will see white. So if 7 different wavelengths are emitted also, all of them will still have a combined maximum at point O. Do you agree with that or not? All 7 colors will have the maximum at point O. Yes or no?
Yes, sir.
So what you will see will be something like this. Just a moment. Let me erase all this. Suppose the screen is here. You will see one pattern of red dots. Okay. Red has the highest wavelength. So the fringe width for red also will be the highest. So the pattern of red dots will be quite wide like this. Are you able to see the red dots on the screen on that white line?
Yes, sir.
Okay, or let me make them slightly bigger. Yeah. So you'll see a pattern of red bands like this. Next, okay, we are assuming both sources emit all 7 visible colors. Okay. Next, you will see a pattern of orange bands. Orange has a slightly shorter wavelength, VIBGR. Orange has a slightly shorter wavelength compared to red. So the pattern for orange dots or the pattern of orange dots will be like this. At central maximum, they'll definitely coincide. At other positions, they may not coincide. But there will be some places where they will eventually coincide. But there will be a difference between the red pattern and the orange pattern. Clear? Next is yellow. Wavelength for yellow is shorter than that of orange. So the pattern of yellow dots will be like this, or the pattern of yellow maxima will be like this. Next is green. Even shorter wavelength, you get a pattern like this. Somewhat like this, roughly. Similarly, other colors also. Let's not waste much time on this. So you can see that at O, all 7 colors will have their maxima forming. Means all 7 colors will be of same intensity at the point O, which is the central maximum. And if all colors of same intensity are incident there, what you will again see is white here. Is this clear?
Yes, sir.
Huh. But if you go away from the point O, okay, for example, uh, fine, let's say you go to this point on the screen. At that point on the screen, red has a maximum, other colors don't have a maximum. Fine. So when you see the pattern on the screen at this position, the color that you see will be reddish. Not perfectly red because other colors also will have some intensity there. Red has maximum intensity there. So red will dominate. What you'll see is a combination of colors, but red will dominate. Is that clear?
Yes, sir.
At this point on the screen, which color will dominate? Which color's maximum is forming at this level? Green's maximum. Okay, the green, we have placed a green dot means that distance corresponds to the maximum of green. So you will see a greenish hue there. Other colors also will be forming, will be present, but green will dominate. Fine. Just a moment, I'll show you the pattern. Right. So when both sources emit white light, the pattern you see on the screen is this. Okay, stop. At the central maximum, you will see complete white, but as you go away from the central maximum, okay, let me stretch this. So Yeah, this is kind of what I was talking about. At the central maximum, you will see it completely white. As you can see, at this distance, there is a reddish hue, red dominates. At this distance, green dominates. Other colors are also present, but green dominates. Okay, that is what happens. Is it clear how you get this pattern when sources are white? Basically, it's an overlapping of patterns formed by all 7 colors. For all 7 colors, the central maximum is the same. So all 7 colors have their maxima at point O. Therefore, at O, you will see a bright white band. But as you go away from O, different colors have maxima at different positions. Fine, we'll stop it here for now. We'll continue in the next class. Next class, we'll solve some more problems based on YDSC and we'll then discuss single slit diffraction pattern. Right.
Thank you, sir.